Hello everyone, welcome to the next part of this lecture. So we reach now in model selection a very important topic called regularization. So regularization in machine learning is very important because it prevents overfitting essentially to the training data. So we want to be able to penalize models that are too complex, any model with too many parameters is probably going to overfit the training data and it's not going to generalize well on new data. So to penalize such models, what we do is we replace the loss function that we just discussed with a cost function, cost of a given hypothesis H. This cost function is made up of the original loss function, which tells you how far you are from the truth, plus regularization parameter lambda times some measure of the complexity of the model, essentially. So the more complex the model, the higher the penalty term and the cost will increase. So this will encourage our machine learning algorithm to avoid models that are too complex. And this will help us prevent overfitting the training data essentially by just adding features. So this will help us reduce the dimensions of the models we're working with. So instead of working with a 10th degree polynomial, which will be heavily penalized by the regularization parameter, maybe this will reduce it to a cubic degree, for example, which in that case will generalize better. And will also help us disregard features that are irrelevant. So the model automatically will assign them a weight of 0 in our final hypothesis. The next topic, we're going to come back to this more in detail later. As you can see, there are many parameters to tune when you're training a machine learning model. So we just saw the regularization parameter lambda. There's also a very important parameter called the learning rate, which really controls how well and how fast you converge to a good model. So, and there are usually many other hyperparameters that need tuning to be able to converge to the best model. So there are different approaches for hyperparameter tuning. One way is to use hand tuning, which is essentially you can imagine that you have a machine with multiple knobs and you're just trying to guess the values for these knobs based on history until you get a model with satisfactory performance. Another way is to maybe put a system in place, which we call grid search. And in that case, we just define a set of combinations that we would like to test. So maybe lambda is 0.1 and learning rate 0.01, and that's one combination. And then create a grid like this and just test all possible combination on that grid, and then pick the model that has the lowest validation error. Or we could just perform random search if there are so many hyperparameters to tune and it's going to take too long to do a systematic grid search. Maybe we just pick them randomly. We can also use Bayesian optimization. So every iteration we run gives us new information. We use that to update our posterior belief about these parameters and test a new set of parameters accordingly. So these are all approaches that we will investigate later on for hyper-tuning these parameters. I want to move next to a topic that's very important, which is the foundation of all the neural network and deep learning we're going to be doing, which is essentially linear regression and classification. So we're all familiar with linear regression, maybe from high school or college. So you have an output y that you're trying to predict based on some observable variable x, and you just assume that the hypothesis is linear in that case, meaning that a model with just two parameters, an intercept omega 0 and the slope parameter omega 1 will be sufficient to get a good model that does well on unseen data. So we're trying to find HW, sorry, it's not omega, it's W, that best fits the training data. And to do that, we want to minimize the loss on the training data. So we want to find the weights W0 and W1 that minimize the empirical loss. So if we consider our loss function to be a squared error, so in that case, actually, we can find a closed form solution for the weights, the optimum weights W0 and W1. So you can see here, we just find the total loss, which is essentially the sum of all the squared errors. So Yj is the true value, and HW of Xj is the prediction from the model. And we find the difference between Yj and that prediction. We square it, and we just sum it over all the training points, uppercase N. And then in order to minimize the total loss, we just take the first derivative relative to W0. So that gives us one equation. And then we take the first derivative relative to W1, the partial derivative. So we get a second equation. And then if we solve these two equations in two unknowns, which are W1 and W0, we get these two formulas, essentially. So these formulas just give you the optimum weights for your linear model. So you can see that, for example, the optimum intercept is essentially the sum of all the true values Yj minus W1 times the sum of all Xj's divided by N, which gives you the average error essentially. And W1 is calculated first using this first formula. Now, maybe we don't want to use a closed form solution. We can replace it with some iterative process. And this is the reason why we're introducing this now, is because neural networks will rely heavily on a gradient descent. So the idea behind gradient descent is that you start with any random values of W0 and W1. So any point in the parameter space. And then we are going to take we're going to make successive modifications to these starting values of W0 and W1, such that in each step we take, we are reducing the loss. Okay, so in order to make this process converge faster, we want to take these steps in the direction that has the maximum possible potential to reduce that loss. And this direction is going to be essentially negative of the gradient, and that's why it's called gradient descent. So if the gradient of the loss function is partial loss of W, partial Wi, then I want to move in the opposite direction of that gradient because I'm minimizing here, and then take a small step in that direction and update my parameters. And alpha in that case is what we call the learning rate or the step size. And this is typically, it's not constant in neural network models. I mean, we have a schedule to reduce the learning rate as we converge to the true solution to make sure that we don't overshoot it. But for this case, you can just assume it's constant. It doesn't matter anyway. We're not taking the derivative with respect to alpha. So if you do that, you get these two gradients. Partial L partial W0 is equal to -2 times Y minus H of X. And then partial L partial W1 is -2 times Y minus H of X times X. So these two gradient formulas, I can use them at any point X and find in what direction I need to take my next step. Now, because I have many training points, so what we do is we actually use all the individual losses, so all the training points. So instead of just calculating this gradient over 1 point, we actually take the sum over all the training points before we take any step. So that's how we are going to do this. So you notice that the first summation here in W0, this is essentially the sum of this gradient right here, y minus hw. So y minus hw. Of course, we got rid of the -2 here. It doesn't matter. It just absorbed in the alpha. So we get the sum of all of this over all the training set, and then we make our move in W0, update W0, and the same for W1. In that case, we just take the sum of this term right here. So if the loss function is convex, meaning it has a global optimum, there are no local minima to get stuck in, and as long as alpha is not too large, so you're not going to overshoot, then this procedure is guaranteed to take you to the optimum values of W0 and W1 that we defined earlier using these two formulas right here. So one epoch in neural network is essentially one run through all the training examples. So every time you do one step, this means that you you evaluated the hypothesis over all the training examples, you calculated the update for W0 and W1, and you took one step. Now, if we're talking about millions of training points, then we don't want to do that. We don't want to wait until we evaluate the function a million times before we take a step. So we replace batch gradient descent with what's called stochastic gradient descent. And in that case, we just randomly select a small number of training examples at each step and evaluate h of w at that small number of training examples. So that's called the mini batch M of size M out of the total number of training examples, big N. And then this allows us to take advantage of parallel operations, parallel vector operations, and run multiple mini batches simultaneously on different threads to essentially do this training operation faster. Now, if I have multiple observable variables, so what if I have multiple independent variables? In that case, instead of a single x, I'm going to have a vector of n elements, depending on how many independent variables I'm working with. And in that case, everything applies except that h then becomes the dot product of a weight vector, w, times the x vector in that case, which is the parameter vector. The best weights, again, minimize the squared error loss, so that's the same as the linear case. And once again, we take the gradient and apply our gradient descent updating rule, which you can see here. So for each weight wi, I'm just going to calculate this sum over all the training points, or if I'm doing stochastic learning, then I'm going to use a random sample of training points to evaluate this on, and then finally this will converge. The second formula here is the closed form formula. The problem with this formula, as you can see, is that it involves an inverse. So if you have 1 million training example, this would involve the inverse of a matrix 1 million by 1 million. And that's why we can do that, and instead we use an iterative procedure like gradient descent. But if this problem is small enough, you can find the correct solution, the optimum solution, the optimum weights, W star, by just plugging in the X and the Y matrices into this formula. Okay, I'll stop here and then I'll see you in the next part.